everybody. This is Carl K9LA, and man, he's got some great attributes in history and ham radio and knowledge. I'm sure you all will be well informed tonight. So yeah, hit him up with questions at the appropriate time, and we'll see what's going on. Let me throw it over to Carl K9LA. Good evening.
Okay, thank you, Rob, and also Jim, and hello to Bob, W6RGG. So how do you know that my April QST article wasn't April Fool's? Oh. Oh, okay. No, it was true, I think. Most of it. Yeah, okay. Let me also answer a question by that was brought up. Paul Gilbert, KE5ZW, was the director of emergency communications. He had to resign because of health problems, unfortunately. And that position was just posted on the ARRL website today. So hopefully someone will, sign up and move to Connecticut. I suppose that's where it's going to have to be, I suppose. Although, a lot of these Zoom meetings, heck, we can work just about anywhere. But let me see if I can share my screen.
Should be able to.
Yeah, gotta find where my mouse is. Yeah, there it is. Okay, there we go. Yeah, Palo Alto, share. Okay, it's gonna come up. Then I'll go to a full screen. There it is. Hold on here. It always takes 2 clicks to get it to go full screen. I'm not sure what's going on there, but yep, there it is. At least for me. It ought to be for you guys too.
Yes, we see it.
Yep.
Okay, well, the title is Space Weather and HF Propagation. Hopefully I'll answer all the questions that Rob kind of put in his email. If not, I'll try and answer them afterwards. There's my email, there's my website. So here's a quick slide. Who is K9LA? Well, I got my novice in October of '61. So I've been around the block a couple times. There's my novice QSL. I enjoy trying to understand solar and propagation topics. I like playing with the antennas. We live in a somewhat rural area north of Fort Wayne, so we can do anything we want. Enjoy DXing. I'm at the top of the honor roll. I managed to work ED, P5/4L4FN, and that got me going to work all the rest of them. I like contesting. Mostly it's casual nowadays. I like fixing and using vintage equipment. There's my novice station, National NC60 receiver, the good old All-American 5-tube design. And that's a DX35. Of course, the VF1, VFO came when I got my general. Graduated from Purdue long time ago. I was an RF design engineer by profession. I retired in 2013 and worked with Motorola in Schaumburg and also Fort Worth, Texas. Then we moved back north into Fort Wayne, Indiana with Magnavox, which went through a whole bunch of name changes, and now it's Raytheon. Same job, just a lot of different name changes. In my early days, I was a airplane and instrument flight instructor, owned a Cessna 170, and enjoyed doing HF mobile in that with a little short whip, and it worked very well. Kind of tough though when you change bands, you had to come down, land, and go back up. Oh well. My wife is Vicky, AE9YL. She got her novice or Tech Plus in 1987 when we lived in Texas. So she's originally was a KB5. And it's really good to have a wife being a ham. That's helps a lot. So here's what we're going to talk about. We're going to quickly get through some stuff on the sun, the ionosphere, HF propagation. Then we'll get into solar cycles, space weather. In other words, what do all those numbers mean and how do they tie to propagation? Then we'll talk about cycle 25, since that's quite a big topic nowadays. A lot of stuff, but we'll get through it. So Here's just a caveat. What we're trying to do is we're trying to simplify very complicated atmospheric and ionospheric processes into simple statements about HF propagation. This kind of works most of the time, but we still have trouble with short-term events. For example, predicting the day-to-day variability of the ionosphere, we really struggle with that. And it shows because our propagation predictions are not daily predictions, they're monthly median predictions. Median implies 50% probability, so they're statistical. We don't have daily predictions yet.
Hey, Carl, I got a comment.
Sure.
Yeah, that's the opposite of the problem the weather people have. Hi.
Yeah, there you go. That's right. Yeah. Okay, and we also have trouble predicting very short-term events, and usually they are enhancements. And if you're in the right place at the right time and catch one of them, wow, that's kind of neat. So here's the sun. That's my favorite star. And there's a picture of the sun in relation to the planets in the solar system. Of course, Jupiter and Saturn are sticking out quite a bit. Earth is one of those little things way in there somewhere. It's a nearly perfect sphere of hot plasma. Plasma is just an ionized gas. It's nuclear fusion at its core. It's about 4.6 billion years old, and it's in the most stable phase of its life cycle. And it's probably going to burn out in about 5 billion years. So if you got some pressing business, you probably got time to, take care of it. Don't worry. Yeah, right. Solar radiation. Okay, there's a plot of the radiation that the sun emits. It emits electromagnetic radiation at many wavelengths. You can see that. The most intense radiation is at visible light wavelengths, which is 400 to 700 nanometers. That's the same as 4,000 to 7,000 angstroms, if you're talking in terms of optical terms. And one thing that needs to be understood is that the energy of a photon is inversely proportional to wavelength. So the shorter the wavelength, the higher the energy of the photon. And it takes quite a bit of energy to ionize the atmosphere. In other words, to strip an electron off a neutral, like an atom or a molecule. Now, if you look at the last bullet, it shows where the important range of radiation for our HF endeavors is. It's very short wavelengths. Follow the green line over. And those are the ionizing wavelengths way over there on the left. So they're much shorter than visible light. And you can see where 10.7 centimeter solar flux is. So 10.7 centimeter solar flux does not have enough energy to ionize its way out of a paper bag. So it's just a proxy for the true ionizing radiation. And we'll talk about that in a little bit. Okay, the ionosphere, that's what enables skywave propagation. And that's one way there in a little picture of discovering the ionosphere. If you get hit by an electromagnetic wave, you must figure that, hey, there's something being refracted from up above those trees. So yeah, don't believe that though. Okay. The regions of the ionosphere, we call them layers, but that's kind of a misnomer. A layer is kind of leads you to believe it's very thin and there's nothing in between the layers, but that's far from the truth. The ionosphere is a continuous electron density, and some regions are peaks in that electron density, some are just inflection points. So the ionizing radiation at those very short wavelengths creates these regions, and it's dependent on the wavelength of the radiation and also the number of neutral atmospheric constituents versus altitude. Now, extreme ultraviolet results in the F2 region, and that's mostly atomic oxygen. That's what results in the free electron. some longer X-rays at 1 to 10 nanometers results in the E region, molecular oxygen, molecular nitrogen, and atomic oxygen. And the shortest X-rays and Lyman alpha spectral line of hydrogen, that creates the D region. So you can see that as the wavelengths get shorter, they can get down farther into the atmosphere. So that's important. And of course, free electrons are what's important for skywave. And there you can see the different regions day and night. And here's some general characteristics of those 3 regions. The F region is roughly 150 to 400 kilometers above Earth. It's the highest in altitude and gives the longest hops. That's what makes it really important. It gives the longest hops for our DXing endeavors. It also has the highest electron densities, and that's best for the higher bands, 15, 12, 10 meters, and even 6 meters. So the F2 region is most important for our long distance QSOs. Doesn't say we can't make long distance QSOs with the E region, but the F2 region is just more efficient. The E region is roughly 90 to 150 kilometers above Earth, above ground. Because it's closer to ground, it results in shorter hops. And also, if the E region gets intensely ionized, like during a summer day, it can block signals from getting up to the F region, which means you can't take advantage of the very long hops that the F region provides. The D region, it's mostly a detriment to propagation because it absorbs our RF as the RF goes through the D region. It's roughly 60 to 90 kilometers. It's the lowest. There's every once in a while somebody mentions a C region, which is a little bit lower, which is I believe due mostly to cosmic rays. And also, of course, the F region can be an F1 and an F2, but most of the time we're talking about the F2 region.
Excuse me, Carl, I think Miko has a question.
Sure.
That's correct. Hey, Carl. Super interesting stuff already by now, and I think it's going to just get better. Quick question about the slide where we just were listing the different regions.
Sure.
I'm wondering, where do these region names come from? Is there A, B, and C region somewhere right above our heads?
Good question. It all started with Edward Appleton back in the early 1900s when we discovered that hey, there's something up there reflecting or refracting our signals back to Earth, and he named it the E region, E for electric. Okay, that's where it all started. So if there was a region higher, it went up to it was called F. A region lower was D. So the origin is the first region we discovered, and it was named the E region because it stood for electric. So does that answer, Miko?
Oh, perfectly. I really wonder, like, how were those? Yeah. I guess we got lucky that nobody found, a dozen layers before below the E one. We would have been in trouble.
Yeah, I've never heard of an A and a B region, and never heard of a G region. So I guess we're stuck with mostly D, E, and F.
Good, thank you.
Okay. So what does it take to make a QSO? Well, 2 things kind of have to happen. The signal must refract back to Earth. If it doesn't, it goes through the ionosphere and it's lost forever. Unless the universe folds back on itself and it comes around in, maybe billions and billions of years, but I don't think we got the patience to wait for it. In other words, the MUF, the maximum usable frequency, must be high enough on the path. The amount of refraction is inversely proportional to the square of the frequency. So what that says is the higher in frequency you go, the less the signal is refracted. It doesn't bend as much. And that's why we need more and more ionization as we move up in frequency. And we need a lot of ionization, especially on 15, 12, and 10 meters. Of course, the amount of ionization is most critical for these higher bands. Now, the signal must also be capable of being detected, and that's determined by all the losses and gains and the noise environment and the mode you're using. If you're using a digital mode, sideband or CW. And one of the things that we usually pay most attention to is ionospheric absorption, and that's in the D region, like I explained earlier. And the amount of ionospheric absorption is also inversely proportional to the square of the frequency. So if you go up in frequency, there's less absorption. And that's why 10 meters has S9 plus signals, when 160 meters can have most signals down at the noise level. It's all about ionospheric absorption. And these lower frequencies, absorption is critical. That's because the MUF is usually high enough. That's because the lower in frequency, the more the wave bends. So in general, we don't care too much about the MUF down on 160 and 80 and kind of 40 meters. We worry about absorption. Unfortunately, we don't have any measurements of it on a daily basis. So just have to do the best we can. And here's distance versus elevation angle. It shows 4 paths. If the angle is too high, in other words, if there's not enough ionization to refract it all the way back to Earth, it'll go through the ionosphere. And that not enough ionization is the same as saying the MUF is not high enough for that frequency over the path. Now, the highest angle that returns to Earth, that's number 2 in that figure, determines the skip distance. In other words, if you have a higher angle than that number 2 path, it's going to go through the ionosphere. So that means nobody's going to hear you in that skip distance zone. Now, ground wave can cover some of that skip distance. Also, lower frequencies can shorten the skip distance too. So it all depends on how much ionization and what frequency you're on. Now, the lower the elevation angle, which is like 3 and 4, the farther the distance. And what that also means is the MUF is higher. It can, so the path number 4 can refract even higher frequencies than path number 3. And path number 4 will go farther. So that's why 10 meters is really a good band to be on when there's enough ionization. In other words, when there's enough sunspots.
One question.
Sure.
How does NVIS work? Is that a different thing than reflection because it's greater than that skip angle, right? Is that a scattering or is that something else? Or
no, it's the same as refraction, just like anything else. It's just that as you go lower in frequency, you don't need as much ionization to refract it back to Earth. It's no different than number 2 or number 3 or number 4. It's just a higher angle at a lower frequency. A great example.
I see. So that's why NVIS works better at lower frequencies than higher. Okay.
I'm very
good
in the traffic nets. And QIN is the Indiana CW traffic net. In February at solar minimum, we have a lot of problem on 80, even on 80 meters, because there's not enough ionization to even refract 80 meters. So we usually move down to 160 and everything's just great. So,
Carl?
Yes.
Yeah, we run an 80-meter net on Tuesday nights, and most of us try to use NVIS. I find NVIS actually works pretty well on 40 during the day. We've done that on field day when we've actually had physical field days. Isn't that mainly the troposphere that we're actually really bouncing that off, as opposed to we're not going as high as the F flares, right? For the low frequency.
Yeah, we are.
Okay.
The troposphere generally does not impact HF. It's not sufficient.
Oh, okay, all right.
So all that NVIS is like on 80 meters, it's, at night, the E region really mostly disappears. So the only thing left is the F region. And it's got to have enough ionization, except for February, deep in winter, at solar minimum, it usually has enough ionization to support the higher angle radiation. 40 meters, of course, the F2 region doesn't go away entirely at night, but it does drop down, and that can hurt 40 meters on the shorter pass, which are higher angles. So, yeah. Interesting stuff. Propagations modes, there are a lot of propagation modes. Multi-hop, sporadic E, trans-equatorial propagation. I believe multi-hop is the most prevalent mode, and there's just a little sketch of what happens. It can be from the E region or the F region. And of course, sporadic E is just phenomenal for six meters during the summer months. It's not too dependent on a solar cycle. And it's best, like I said, during the summer months in the late morning and early evening. That bimodal probability, late morning and early evening, allows a very long distance QSOs. And at least here I know the East Coast has had just a wonderful sporadic E season. The Midwest, kind of, not too bad. You guys probably had some good JA type openings. I don't know how prevalent they were, but at least all the people on the East Coast say this was a great sporadic E season. Well, what do they know, right? Solar cycles. Okay, that's going to determine which bands are open. And there's just a picture of the sun when we're at solar max, a lot of dark spots, which are sunspots. And solar min, there's nothing. We just came through a very long solar minimum. And there were lots of days when there were nothing there on the sun. So what's a solar cycle? You probably know all of this. It's also called a sunspot cycle. It's from the time from A to B to C. It's about 11 years on average. Some are shorter, some are a little bit longer. On average, the rise time from A to B, from solar minimum to solar maximum, is about 4 years. And the decline is about 7 years. So 4 plus 7 is the average 11-year solar cycle. Solar cycles are important for HF, the higher bands, 15, 12, 10, and 6, because the area around sunspots emits extreme ultraviolet radiation. And remember, that's the true ionizing radiation for the F2 region. So sunspots, just like 10.7 centimeter solar flux, sunspots are just a proxy for EUV. But we do have very good correlation on a long-term basis. Not daily, but on a longer term basis. The more sunspots, that means there's more EUV radiation coming from the sun, which means there's more ionization in the F2 region. And that gives the best propagation on the higher HF bands, 15, 12, 10, and even 6 meters at times. On the other hand, solar cycles are important for the low bands, 160, 80, 60, and 40. When we have less sunspots, there's less ionospheric absorption. In general, there are less disturbances to propagation. So that gives the best propagation on the low bands. And roughly speaking, 30, 20, and 17 are generally good throughout a solar cycle. And one thing I remember, I don't know who said it, but many, many, many years ago, if you only can put up one antenna, put it up for 20 meters, because that band will be good throughout a solar cycle. And that's true. And 30 and 17 are kind of in the same ballpark. So when are the bands open? Here's just a quick summary. The lower bands are best at night because absorption in the D region minimizes. The middle bands, 30, 20, 17 are generally okay day and night. The higher bands are best during the day, and the MUF, the maximum usable frequency. In other words, the amount of ionization needs to be high. 6 meter propagation via the F2 region is best at solar max in the fall and winter months. Don't forget sporadic E in the summertime. And the higher bands generally follow the sun during the day. In other words, in the mornings, you should point, if you got a directive antenna, you should point it towards the east, northeast through southeast in the morning. Then around noon and early afternoon, you should point it southeast through southwest. And then in the late afternoon and evening, if there's enough ionization, you should point it from southwest to northwest. Very general statements, but seems to work pretty good. And the digital modes have an advantage over sideband and CW. If you're working FT8, you probably know that. A lot of times there's FT8 QSOs going on and nothing on sideband and CW, even though people are trying on sideband and CW. And I'm pretty sure this solar minimum will go down in history as the most active on the higher bands due to the digital modes. If we didn't have the digital modes, boy, the higher bands, 15, 12, and 10 would be, nobody'd be there. So the digital modes have, it kept activity on the higher bands going through our solar minimum period. Okay, now we get into the space weather stuff. And there are lots of sources of space weather. TAD, K7RA puts out a weekly bulletin on the ARRL website. NW7US, who lives in, let's see, where's he live now? Hold on here. I got to wait for some good neurons to fire. He's not in Seven Land, that's for sure. Oh, I think he's in Southwest Ohio. So I'm not sure what he's doing there, but whatever. And Frank, W3LPL, gives a prognosis of propagation in Bernie. W3OR is the daily DX. And there's a lot of information there. Dr. Tony Phillips runs spaceweather.com. Lots of good stuff there. Not only data, but good stories too. The Space Weather Prediction Center, which is part of NOAA, they have a more technical website with lots of data, not too much text, but lots of data. The E3EN has solarham.net, again, lots of data and some text explaining stuff. Of course, there's Dr. Tamitha, the Whiskey X-Ray 6 Space Weather Woman. She has her videos, talks about solar stuff and propagation. And N0NBH has a banner, a colorful banner. There's his website. This banner shows up at, for example, QRZ.com and many other places. And that's what we're going to focus on from now on for the remainder of the presentation. Because I believe all the data that's there will suffice for trying to understand what the heck's going on. So there's a picture of the banner. I downloaded it this morning, and the parameters that I think are important are enclosed in the gold boxes. Now there's the key fact. When the solar flux is 65, in other words, we're at solar minimum. When the sunspot number is 0, no sunspots, there's still enough extreme ultraviolet for 20 meters to be open during the day and early evening. So what that tells us is SFI, the solar flux index, SN, the sunspot number, and 304A, which is an extreme ultraviolet measurement at 304 angstroms or 30.4 nanometers. Those three parameters can indicate which of the higher bands may be open, depending on how far above they are at their solar minimum values. The Ka, B sub Z, and SW, they tell us how disturbed the F2 region may be. So let's get into a little bit more details here. So the SFI is the latest 10.7 centimeter solar flux index. It ranges from about 65 at solar minimum all the way up to 300 at solar maximum. And of course, how big the solar maximum determines exactly how much. Is it 300, is it 350, 250, whatever. But you can see there's quite a range there going from solar min to solar max. SN is the sunspot number. That's today's sunspot number. It can be 0 at solar minimum. We saw lots of those in the past several years. And it can get up to about 350 at solar max. 304A, that's, like I said, extreme ultraviolet at 30.4 nanometers. It's around 90 at solar minimum and goes up to about 400 at solar max. Now, there was another parameter, MUF-US Boulder. What that is the maximum usable frequency over the Boulder ionosonde, assuming it's the midpoint of a 3,000 kilometer path. So let's take a look at some of that. The SFI is 74. Now remember, at solar min, it's about 65. So we're more close to solar min than solar max. Sunspot number was 36. Again, we're closer to solar min than solar max. 304A is 113. Remember, at solar min, it's usually about 90 and goes up from there. So we're a little bit better than solar min. And the MUF-US Boulder was 15.61 megahertz. In other words, if Boulder was the midpoint of a 3,000 kilometer path, 20 meters should be working because it's greater than 14 megahertz. And that was at 1332 UTC, which it's only about 9:30 in the morning here. So that'd be about 6:30 in the morning out your way. So as the day progressed, I'm sure the MUF got even higher. So interesting stuff. So now let's get to the parameters that tell us how disturbed the F2 region may be. The K index, it's a 3-hour index. It's logarithmic. It goes from 0 to 9. 0 is quiet, 9 is very disturbed, and it tells us how active the Earth's magnetic field is, because the the activity of the Earth's magnetic field can screw up the F2 region, and that will cause our bands to be disturbed. And generally that's going the wrong way. Now, sometimes you see a P appended to the K and the A index. That means it's a planetary index, which means it's from kind of an average of many stations. And what it's trying to do is give you a worldwide view of the Earth's magnetic activity, as opposed to the K index or A index from a single observatory. The A index is the average of the 8 3-hour K indices. And it's a linear scale. It goes from 0, quiet, to 400, very disturbed. BZ is the strength and direction of the interplanetary magnetic field. In other words, basically the sun's magnetic field. Goes from about plus 50 to minus 100. What it is the Z component is parallel to the Earth's north-south magnetic field. So it's going to tell us how the interplanetary magnetic field couples into the Earth's magnetic field. If there's good coupling, that's not good for our HF propagation stuff. And SW is the solar wind speed. It goes from about 300 to 2,000, average is about 400. So here's some details about what we should expect as the solar flux, the sunspot number, and the EUV start going up. For example, at solar minimum, like I said before, the extreme ultraviolet's about 90. The long-term sunspot number is about 0. We're at solar minimum, and the 10.7 centimeters solar flux about 65. And generally the MUF is about 20 megahertz, which says 20 meters should be open okay. 17 meters even should even be open, but kind of a fewer number of days in the month. Remember that median implies 50% probability. So that 20 megahertz means the MUF would be at least 20 megahertz on half the days of the month and less than 20 on the other half. Unfortunately, we can't really tell very well what it's going to be on each day. So when okay, let's look at the long-term EUV. If it's up at 285 and the sunspot numbers are around 179 and the solar flux is 170, that's kind of an average solar cycle, the peak of an average solar cycle. Cycle 23 was that. And you can see that the MUF has increased significantly. It should give some good 10-meter propagation. Still, it's too far away from 6 meters. And 6 meters, that's the bottom row. If the EUV is up at 400, the sunspot number is up at 286, 10.7 centimeters solar flux is at 245. That's a big cycle. Cycle 19 was the biggest in our recorded history. And the monthly median MUF could be about 46 megahertz. That means 50% probability. Now, a little less probability would give 6 meter propagation. So that's a good chart just to judge of where we are as cycle 25 rises. And Ka, B, Z, and SW. For an undisturbed F2 region, we desire K less than or equal to 3, which translates to an A index less than or equal to 15. It's okay if we prefer the BZ to be positive, which means that the interplanetary magnetic field is not coupling very well to the Earth's magnetic field. A little negative is okay, but nothing major. And we'd like the solar wind speed to be not too much greater than 400. Now, although the solar flux and the sunspot number and the EUV parameters may indicate there's enough ionization, the above parameters, the Ka, Bz, and Sw may say that the band is screwed up. In other words, the MUF really isn't as high as those parameters indicate. So we have to remember that MUF US boulder tells us everything. You know, it includes what's going on with the Earth's magnetic field. So that's a very good indication of this general propagation, at least in the continental US. There are disturbances to propagation, and I've listed them in order of severity. Geomagnetic storms, they last the longest. They can last several days, up to a week, and really screw things up. And the K index is elevated, and the F2 region is disturbed. And generally, that means the maximum usable frequency goes down. Geomagnetic storms are caused by coronal mass ejections, which are most prevalent around solar max, and coronal holes, which are most prevalent in the declining phase of a solar cycle. So we're kind of in the quietest period of a solar cycle because we've passed the declining phase and we're starting to go up a little bit. So the Earth's magnetic field will be quietest, which means it doesn't screw the F2 region up as much. There are solar radiation storms, which are caused by big solar flares of M and X class. which usually happen around solar maximum, but they can happen anytime. And what they do is a big solar flare can emit relativistic protons. In other words, very high speed and high energy. And what they do is funnel into the polar cap, and they can degrade over the pole pass. And of course, your path to Europe is one of those examples. Radio blackouts, they're also caused by a big solar flare, because a big solar flare could also emit very short wavelength X-ray radiation, and that increases absorption on the day side of the Earth. So just something to look at. Oh, I should have mentioned way up front that I will send Rob a PDF of this presentation too. So whatever. So what about real-time QSO data? Well, one of the ones that I kind of like to look at is dxmaps.com. And this is just a picture on April 13 this year. And it's from 1554 to 1644. And I picked 17 meters on a worldwide view. And you can see that a lot of people were working a lot of stuff. North America's working Europe and South Africa, even into the Pacific. Europe was working South America. So it gives a very good picture of what's going on right now. And you can kind of bypass all those numbers and just go to dxmaps.com. There's similar info at PSK Reporter, WhisperNet, the Reverse Beacon Network. You can transmit specific formatted signals and then see where you're being received in the world. Kind of, real-time propagation. And of course, there's the IARU NCDXF beacons. They're on 2015, 2017, 15, 12, and 10 meters. And there's 18 of those around the world. So in a 3-minute period, you can tell what worldwide propagation is like on a specific band, one of those bands. So it's very helpful. And there's software that helps you pick out those signals and even shows pretty interesting openings when you start looking into that, into the details there.
Carl, I believe we have a couple of questions from
Okay.
Daryl and Miko.
Okay.
Go ahead, Daryl.
Yeah, hey, Carl, you already said you're going to send the PDF. That was one of the questions I had, so thank you. But second question is, on the, like, if you look at the banner, like on QRZ, the MUF folder, I see MUF, but I see it looks like a sliding scale, so to speak, to the, is that what you're talking about? Is that the MUF folder, or is it?
No, MUF folder's at the bottom on the left.
On the bottom at the left.
In the gold box.
Let me go back.
Opposite the sun.
Yeah, left of the sun picture.
Oh, MUF US folder. Oh, okay. I'm visually impaired, so I completely just missed it. Thank you.
Yeah,
That's
that
okay.
MUF is more for VHF conditions.
Yeah.
Yeah.
So we're saying that 15.61 megahertz is essentially what that's saying, right?
That's right. Yes.
Okay. So barely over 20 meters, but 20 meters is open.
Yep.
Okay.
Should be, yeah.
Well, we think, yeah, exactly. Remember, 50%, 50%.
No, that's a real-time
Oh,
measurement.
that's a real time? Okay.
No, it's not a predicted monthly median. That's a real-time measurement.
Oh, okay. All right. Thank you very much.
Yeah, it takes into account how screwed up the Earth's magnetic field is too. So it tells you everything. But just in the continental US, basically. So, okay. Next, Miko.
Yeah, question regarding, I think it was the next slide. You listed the different kinds of solar particles and different types of radiation. My question was, which particles or what type of radiation is responsible for the visible aurora phenomena?
Okay. Yeah, I didn't mention that at all, but aurora is due to the Earth's magnetic field being disturbed, and there are trapped electrons in the radiation belt, and they come and funnel into the high latitudes. So it's electrons that are precipitating into the polar regions, and that causes aurora. So it's nothing right from the sun. It's electrons that are trapped. Of course, they originally come from the sun, but aurora is not particles directly from the sun. That's kind of a myth that's out there.
Okay, so what happens with the sun? So it's not solar particles. Is it the magnetic flux, or what are we being sort of bombarded with?
Well, it's the solar wind will screw up the magnetic field, the Earth's magnetic field. It's like a shock wave, I guess you could say.
Okay.
The streaks are the streaks of light that you see, those are probably coming from the electron interactions, and the electron interactions are caused by the magnetic field. Is that something like what you're saying? Am I understanding right?
Yes. Yeah, like when a coronal mass ejection occurs, that's going to speed up the solar wind. And when that solar wind hits the Earth's magnetic field, it can cause the release of electrons that are trapped in the radiation belts, and those electrons funnel into the polar cap. And as they precipitate downwards, they excite stuff and cause all those visual displays.
Okay, yeah, good stuff. Thank you.
Okay. Okay, propagation right now. So what's going on right now? Here we are in August 2021, and we're just starting to see cycle 25 rise. I left out the number 25. I'll put it in before I send it. On 160 and 80, local QSOs during the day, NVS at night, domestic and worldwide QSOs at night. Probably need a good station for that, although you can work quite a bit of stuff. Interesting, you generally think of 160 as a very local during the day, but with a decent station, I can work East Coast around noon on 160 on CW. So the signals are there, and you just gotta be able to receive signals that are kind of close to noise, and probably use a kilowatt too, or 1.5 kilowatts. 60 and 40 meters right now are local QSOs during the day, domestic and worldwide at night. 30, 20, 17 worldwide and domestic QSOs during the day and early evening. As cycle 25 gets bigger and bigger, we'll probably see more QSOs extend into the evening hours, especially during spring, summer, and fall. 15, 12, and 10, occasionally we'll have some north-south QSOs now. You got to temper that with the fact that the digital modes are going to provide more opportunities. And especially watch for better propagation on the higher bands this fall and winter due to the change in the atmosphere, which results in more F2 region ionization in the fall and winter, and the fact that cycle 25 is rising too. So that's got to help. So I think this fall and winter is we're going to be kind of seeing what's to come. So cycle 25. If you've only been licensed for several years, you may be asking, what's so great about those bands, 15, 12, and 10? Most of the time there's noise and not many signals. Now, all I can say is wait a couple of years and you'll be amazed what those bands can do around solar maximum, especially with low power and modest antennas. And if you've been through even cycle 24 was kind of small, but we had some really good 10-meter propagation in 12 and 15. So here's a little graph that says our historical data tells us that big solar cycles rise faster than small solar cycles. So here's a plot of cycle 19 in blue. That's the biggest in our recorded history. plot of cycle 24 in red, which is a pretty darn small solar cycle. And green is what cycle 25 is doing right now. It's rising, looks like it's rising a bit faster than cycle 24. And that kind of suggests that cycle 25 is going to be another small one. In fact, I'm aware of 56 predictions for cycle 25. 50 are for a below average cycle. Dr. Scott McIntosh and his colleagues have predicted, initially predicted a very big cycle. They just recently downsized their prediction a bit because of what's going on. And we'll just have to wait and see what happens. Dr. McIntosh is going to be talking at the Pacific Northwest DX convention this Saturday. He's on at, I think it's 4:15 Pacific time. So it's free, it's a virtual. So you may want to go take a look at that. But right now the data says that cycle 25 is going to be small unless something very interesting happens. So what can we expect if cycle 25 is similar to 24? Well, on the left is cycle 24. The black data is the monthly mean solar flux. You can see it's kind of spiky. So the purple is smooth. That's why we further average the monthly means, and it results in a more smoother curve. And that's purple. You can see there, obviously, there were 2 peaks in cycle 24. On the right is red is this prediction by the solar cycle 25 prediction panel of NOAA. They're predicting cycle 25 is going to be kind of similar to 24. Will there be 1 peak or 2? Yeah. I'll let you know in about 5 or 6 years. And the green lines are what we need the solar flux to be for 10 meters and also 15. And it comes from the chart that we went through earlier. You can see we still have a way to go before 15, 12, and 10 open on a daily basis. Now, what you got to do is watch out for a big spike in solar flux or sunspot number or extreme ultraviolet, or for a small spike in the K index, because you may be rewarded with a short-term enhanced opening. So here's a big picture. This comes from solen.info/solar. And the data is from August 31st, 2020 to the present. The black data is the solar flux, and you can see toward the end of 2020, the sun hiccuped, lots of sunspots, solar flux increased, and we had great worldwide conditions for CQ Worldwide DXCW contest at the end of last year. And then things settled back down to solar minimum conditions. We had another kind of hiccup, a couple hiccups, and there was some enhanced propagation. So you got to remember that it's really the extreme ultraviolet is the true ionizing radiation for the F2 region. So this sure suggests that if you see this happen, you ought to go see what's going on in those bands. And if there's a spike in the K index, a good example was the October 2018 California QSO party. On Saturday of the contest, I took a look at the Boulder maximum usable frequency. Boulder's about halfway between California and the Midwest here, and you can see the MUF was only about 20 megahertz. So I didn't hear any W6s on 10 meters on Saturday. But on Sunday, the K index spiked up. It didn't go, way up, but it was a good spike. And you can see what happened to the MUF. It went up to a little bit more than 30 megahertz. There were lots of W6s to work on 10 meters. So these short-term events are interesting. We just can't predict them. But if you see it happen, start checking out the higher bands to see what's going on. So summary, all I can say is get on the air and operate, because experience is a great way to gain knowledge of all this. You can make QSOs and contests, worked all states, the XCC, worked all zones, and especially have fun on 15, 12, and 10 when cycle 25 has more sunspots. Like I said before, just kind of monitor the data. If you see a big spike in the solar flux or a small spike in the K index, go see what the higher bands are doing. And of course, use the digital modes because they offer more opportunities because they can hear signals farther down into the noise. And there's a couple of references on the Little Pistol's Guide to HF Propagation by NM7M. The book's out of print, but it's on my website. You can download it. It's 15 megabytes. It's probably not too big nowadays unless you got dial-up, and that'd be a problem. Sure. But it's a good, very readable book, and whatever. There's a CQ shortwave propagation handbook, very recent update of the 1995 edition. So, Rob, that's all I had. Rob and Jim. And so, if there are any other questions, yeah.
I think Daryl has a question there for
I
you.
was just gonna ask, so there's no way to order more sunspots?
Oh, I did. I ordered them from Amazon, but they put them
They
on
didn't
back.
deliver?
Put them on back order. Yeah, I don't
Oh,
know. I
man.
keep reading about that. Yeah.
All
Even
right.
HRL says they couldn't, they said they were trying to get them, but I guess they're back ordered. I don't know. Anyway.
Right.
I think it's a worldwide problem there, Daryl.
Yeah, it could be. Yeah.
In short supply. Carl, that was fascinating. I've never paid any attention to this stuff, but I'm going to start doing so.
Okay. Yeah, the good thing to do is just listen every day, or if you got Packet Cluster or something, or go to dxmaps.com and see what's going on. And whoa, hey, the band's open. Better get on there and have some fun.
Carl, I got a question.
Sure.
I'm not too swift in this propagation thing, but what would be the one or two values that would be most significant if you were tuning around?
Values, you mean like the solar flux?
MUF and
Yeah. Oh, the Boulder MUF on that N0 NBH banner tells you everything, really. And of course, it's going to vary throughout the day. Generally get higher as you approach noon and early afternoon. So that will give a good indication, at least in the continental US. It may not, be too good for worldwide stuff, but there are other websites that can tell you what the worldwide ionosphere is doing right now, not just, over Boulder. What I can do is I'll add that to the presentation here. And
okay, thank you.
yeah, and just wait for higher solar flux, higher sunspot numbers. Yeah.
The question, W6APZ, according to your graph, the 10.7 centimeter solar flux was all the way to the right from the maximum radiation on the chart that was to the left. So why is 10.7 centimeters used?
Okay, what chart was that? I kind of got lost.
Okay, one of your earlier charts, you indicated where the maximum radiation occurred in the solar flux. And the 10.7 was all the way to the right, but the maximum radiation was all the way to the left. Maximum the frequency of maximum radiation that caused ionization of the ionosphere.
Oh, you mean hold on here.
Nope. Further back. Yeah.
That's the start of it right there.
This, not this chart.
Yeah, that's it.
Okay.
Notice ionizing wavelengths all the way to the left, and 10.7 is all the way to the
Yep.
right. So why
Which
was
says-
10.7 chosen?
Yeah, why was, well, okay. Okay, sunspots. Our record starts about 1749. And you got to realize that sunspots are counted by humans. So it can be a very subjective measurement, and there's been problems there with observational bias, et cetera. So the 10.7 centimeter solar flux is measured by a receiver and an antenna system. So there's no human bias in there as long as everything's calibrated correctly. It started in 1947 when radars were available from World War II, and they happened to be on 2,800 megahertz. That's 10.7 centimeters. So that's why we measure 10.7 centimeters, and it is can correlate very well to extreme ultraviolet on a long-term basis, not on a daily basis. But 10.7 centimeters is preferred because it's an objective measurement. Unfortunately, it only goes back to 1947, whereas sunspots go back to 1749. So if you're doing study on what propagation was during like the Civil War, you have to use the sunspots, right? Yeah.
Thank you.
Yeah.
Question about ES propagation. It seems like ES is much more common over Europe. I know there's a lot more. I mean, weak signal VHF is just much more popular in Europe. So maybe they just detect the ES sort of openings better than we do here in the US. But even discounting for that factor, it still seems that Europe gets a lot more, 6 meter openings through ES. Is that the case? And is there any info on why that might be happening? Well, I mean, otherwise, like F layer propagation, it's a global phenomenon. We all get the radiation from the same sun, so it doesn't matter sort of where you are.
And I have one comment on that. It could be that Europe is generally of a more northerly latitude than the continental United States.
It's very obvious from the data we have that sporadic E is not an equal opportunity mechanism around the world. We don't fully understand, we're pretty sure it has to do with meteors ablating in the atmosphere, and then somehow those electrons get assembled into very dense and thin layers. The magnetic field comes into play. And what we're learning just recently is events in the troposphere, well below the E region, can couple up to the E region and cause sporadic E. G3 YLA, Jim Bacon, he's a retired meteorologist with the BBC, looks at tropospheric weather, and it's uncanny, his prediction of ES compared to what's going on. Now, mostly it's between the East Coast North America and Europe. And that's another good slide to include when I send it to you. So there's probably stuff we just don't know yet. Why it happens here and not there. And it even seems, if you look in the data from the 50s, that where sporadic E occurs has moved a bit when you look at it in nowadays. So I just don't think we understand it all yet. So I don't think I can give you a specific answer.
But I mean, I think there is a reason we call the Northern Lights, which is to happen in the north. And the effect of these propagation is not going to be, or I'd say latitude is going to affect
Yes.
or be an important variable.
Oh, yeah, you bet. Yeah. You know, if what's going to happen one day when we fully understand sporadic E and we can predict when it's going to happen, well, we won't have to call it sporadic anymore, right? Yeah, yeah. It's got a good name right now.
Yes, it does. Has there been
A
any
question.
research regarding impact that rockets fired into outer space have had with respect to their exhaust plumes and so forth?
Oh, you bet. You bet. Yeah, we can see the signature of a rocket going up in the ionosphere. Yes. In fact, I remember another paper that had we could see the signature of an underground nuclear explosion by North Korea. So yeah, that happens. There's lots of stuff going on, and we don't have probably a good handle on everything yet.
The gray line communication, is there anything particular about the gray line, or is it just a matter of timing that is that a particularly north-south phenomenon is the question?
Well, it's yeah, gray line was first reported, I think it was in 75 by let's see, 3 6s, right? Shoot, I can't remember their calls, but and what they discovered was 80-meter long path into Europe was very good when their path to Europe was kind of aligned with the terminator being the division between daylight and darkness. I'm not sure we fully understand it yet, but of course, what you can say is, you know, there's on the dark side, the D region is down. On the daylight side, the D region is up, and it probably has a lot to do with absorption. On the higher bands, it's really mostly an MUF issue. When the daylight occurs, the MUF goes up, and that allows the path to happen. But you should always check for gray line when gray line conditions occur between you and the target you're going after, because you may be pleasantly surprised.
Although we talk about the northern lights in the northern part of the world, there's also the southern lights, which happen below the equator.
Yep. Yeah, over Antarctica, in general, since the electrons that are trapped and start flowing into the polar cap come within the Earth's system, that means both the northern aurora and the southern aurora are kind of similar. They happen, you know, kind of simultaneously. So yeah, there are southern lights, aurora australis, I think it's called, right? Or however you pronounce that last word. But yeah, there are northern and southern lights. Just not enough people down in the southern portion, though.
Any other questions for Carl? Well, hearing none, Carl, I appreciate your time tonight. That was a wonderful presentation.